So we're going to try and ease into the discussion of exponential and logarithmic equations this way. It happens to be that time of year where a lot of people turn their attention to so-called March Madness, and they fill out brackets. Now, a good question would be, well, you've got 64 teams, ignoring the play-in. How many games are going to be played, though? If you add up each round and keep on going, how many games are going to be played? And you can easily kind of add it up, but you can approach it cleverly. Think about it this way. You play a game, in every game, everyone has a loser, right? How many losing teams are there in the NCAA tournament? There's a game for each. 63, right? So there's going to be a total of 63 games played. Now, much is made about the odds of winning the NCAA bracket or filling out a perfect bracket. It's just probably never, ever, ever going to happen in our lifetime or our children's lifetime or their children and so on and so on and so on, because the odds would be really, really small. So let's see how small they would be. It'd be 1 over 2 to the 63rd power. And let's just kind of look at 2 to the 63rd power, try and get an idea of that. That's going to be a pretty big number. So 2 raised to 63rd. Wow. Does anyone recognize what this is? Yeah, it's a number in scientific notation. So it's 9.22 times 10 to the 18th power. In other words, if I wanted to figure out what that number is, I'd start moving this decimal place 18 spaces to the right. So 220. So that's 6, 9, 12, 15, 18. I'm not even sure my vocabulary goes that high. Let's take a look here. That's millions, billions, trillions, quadrillions, quintillions. That's huge. That is really, really huge. If you were able to count one number a second 24/7, it would take you 30-some years before you'd reach a billion. So you're talking about several orders of magnitude much bigger than that. Not going to happen. So the possibility of a perfect bracket, no, not going to happen. But it's always kind of fun to try. Now let's, oh, my ride's here. Sorry, gotta go. So let's play around a little bit more with some big numbers. The largest prime number typically known, let's see here, is called a Mersenne prime. So it's always going to be 2 to some power minus 1. So a very simple Mersenne prime number would be 2 to the 5th power minus 1. 32 minus 1 is 31. And typically the largest prime number known is a Mersenne prime, because they're easier to check in special ways. But the largest one known is a whopper. It's really, really big. So let's take a look at that one. The largest Mersenne prime known is 2 to the 77,232,917 power minus 1. Wow. So a good question would be, how many digits are in something like that? And to understand that, let me start moving this conversation back to logarithms, and eventually we're going to use logarithms to solve exponential equations in section 11.7. So right here I've taken the logarithm base 10 of this number, and I get 1.2. And what you can notice about these numbers is that the number of digits is increasing. Let's take the log of each of these. And there's a nice little relationship between the number of digits and this number here. For instance, this has 2 digits, I got a 1 here. This has 3 digits, I got a 2 here. So if you want to know how many digits there are in a number, you can take its log, right? So if I had a 7-digit number, what would its log be? What would the number to the left of the decimal be? Yeah. Actually 6, right? Yeah, so if I copy this here, put that there, yeah, it should be a 6. So 1 plus the number of the logarithm tells you how many digits there are. Well, that's kind of a big thing for our Mersenne prime. That's going to be 2, in fact, I think I got it right down here, 2 to the 77,232,917. And when I hit enter on my calculator, it doesn't like that. So if I want to figure out how many digits there are, then I'm going to take the logs. And this is kind of a reminder of one of the properties that we're going to use when we solve exponential equations. And it's the important property that gets a lot of work done for us. So if I want the log of 2 to the 77,232,917 power, and I can't calculate this number directly, what I can do, though, is I can use our properties of logs. What property of log helps me out here? The power rule, yeah. So I can take this and bring it out in front, and then I get 77,232,917 times the log of 2. And even though it's going to be a big number, it should give me, should be able to give me an answer. Let's take a look here. 77,232,917 times the log of 2. So from what this is telling me, this number, let's see, let's write it down here, 232,494,24.67. We'll ignore the 0.67. If we add 1 to this, 425, 249, and 23. So what it's saying is that the largest prime number known would have 23-some million digits. Wow. But the bottom line for us is that this property of the exponents is going to get a lot of work done for us in solving exponential equations. Exponential equations are equations that are going to have something in the exponent. So we're going to start solving that. This is section 11.7. By the way, this is, like I said, it's a Mersenne prime. So keep an eye on that for maybe some extra credit. We'll start with problem number 30. Has everyone got calculators today? Okay. Problem number 30 is 5 to the x equals 12. All right. Now the problem is you can't take the square root on both sides to get x by itself. You can't raise both sides to the 1 over x power. That wouldn't work either. What you can do, though, is you can take the log on both sides. So let's do that. I'll do the log of 5 to the x equals a log of 12. And as long as I'm taking the log on both sides, I'm okay. Now, it was kind of a long-winded introduction, but the big point of part of what I did was to remind you of one of the properties of logs, and that is this term can come out in front. So it's going to be x log of 5 equals the log of 12. Okay. Well, we want to solve for x. What do you have to do to solve for x? Divide by the log. So it's going to be log of 12 divided by the log of 5. And that's it. So let's take a look at that numerically. Do it on our calculators. So we'll clear this out. We've got the log of 5, excuse me, log of 12 divided by the log of 5. There we go. So our solution, if we were to round it to, say, the third decimal place, would be about 1.544. But how can I check that? If I was looking at that saying, I wasn't really happy with my score on the last test, I want to make sure I do well on this test, how could I check that? What do you think I could do? Yeah, plug it in for x. I should be able to take this number, put it in here, and get 12. Now, there's a clever way you can do that. On your graphing calculator, there's this little key called answer, and that holds this number in its storage. So if I want 5 to that power, I can do 5 raised, so that's this key here, 5 raised to the power of answer. What do I have to do to get to the answer button? Thank you. Second, and then the opposite key. So 5 to the power answer should give me exactly 12. Now you can kind of cheat a little bit if you want to. You can do 5 raised to this power. You can go up here and capture that. It might not be exact. It's pretty close, though. It should be convincingly close. And, you don't even have to necessarily do anything fancy like that. You can just try your rounded answer, 5 raised to the 1.544. Again, should be reasonably close, convincingly close. In any case, you can check your answers. Now, what's going to happen as we go through these things is that these types of problems are going to become a little bit more involved, and it's going to keep on building on itself. So try and hang with me. If you have some questions, please let me know. How are we looking on the first one, though? Good? Good? Okay, thank you. Let's try problem number 38. 5 to the x plus 1 equals 3. Okay. Same kind of problem that we had just a minute ago. A little bit more work. Start by taking the log on both sides. So I'll take the log of 5 to the x plus 1. And that's going to equal the log of 3. Then what? And it is. Yeah. Thanks, Hassan. So the x plus 1 comes out in front. Let's keep that in parentheses. So it's going to be x plus 1 times a log of 5 equals a log of 3. And we'll divide both sides by the log of 5. That's not going to kind of complete everything, but it will help out. Almost done. What's the last thing that I need to do to get x by itself? Yeah, subtract 1. So I get x equals a log of 3 divided by the log of 5 minus 1. Now that minus 1 is kind of by itself. Don't subtract that 1 from the log of 3 or the log of 5. It's just kind of by itself. There's actually a lot of variety in the types of answers you can get here. It kind of depends on how you solve this. Some people right here are going to want to distribute. We didn't need to distribute in this case, but there will be one coming up where we need to distribute and then solve. So, is it worth it to take a second and distribute and see what would happen if we distribute? I got a couple of shakes of the head. I'm getting conflicting information. You can decide. Sure? All right. So let's revisit 38. So it was 5 to the x plus 1 equals 3, and then log of 5 to the x plus 1 equals log of 3. I brought the x plus 1 out in front. Equals log of 3. If I distribute this, and it's natural to want to distribute. We've done it solving linear equations for a long time. This is x times the log of 5 plus the log of 5 equals log of 3. You look at this and you're like, all right, well, I want the x by itself, so I'll move that to the other side. And when it changes sides, it changes signs. Good. So that's going to be x log of 5 equals a log of 3 minus the log of 5. There's one last thing to do here. What is it? Divide by log of 5. X equals log of 3 minus log of 5 divided by log of 5. And that might look a lot different than our previous answer, doesn't it? And our previous answer was this. So are they the same? They should be the same equation. The way to see that they're the same is to realize that to combine these things, I would actually need a common denominator. And the denominator would be the log of 5. So I could write 1 as the log of 5 divided by the log of 5. And now I've got a common denominator. I can pull them together like that. So they are the same. Whichever way you solve it, I'll be happy. So if you want to solve it like this, leave me an answer like that, that's great. If you prefer to do it this way, that's fine too. Is it worth it to practice checking this one on our graphic calculators? Okay. Let's see. Which way do you want to calculate things? You want to calculate it from here, or do you want to calculate it from here? Pink or blue? Pink? All right. I think that looks easier. So let's do the log of 3, parenthesis, divided by the log of 5. Log of 5. And a parenthesis. You need that closing parenthesis. Minus 1. And that goes into answer. Well, to check that, I want to put that back in my original equation and see that 5 to the answer plus 1 gives me 3. Let's check that that happens. 5 raised to the power of answer plus 1, bam, exactly 3. So it's kind of nice that you can double check these things before you hand in your exam. Bless you. Any comments on that one? Yeah. Sometimes they'll ask you for a decimal value, but not on every problem. A lot of times they'll just say, solve it. Yeah, so the decimal value here was approximately negative 0.3174. So those little squiggly equal signs means approximately equal to. Well, let's keep going. I think the extra practice on that last one with distributing was well worth it, because we're going to need something like that in problem number 34 here. Six to the x equals 7 to the x minus 4. Wow, double duty here. Again, this is an exponential equation. Can you see why we're calling them exponential equations? How would you define what an exponential equation is? If one of your friends is taking maybe beginning algebra and is looking up to you, like, ooh, hey, heard you're solving exponential equations. What's that? What would you say defines or characterizes an exponential equation? What about the exponents? They're there. That's true. They are there. What's that? What's in the exponent? A variable. Yeah. Yeah, there's a variable in the exponent, right? That's what characterizes something as being an exponential equation. And the way we get rid of that variable in the exponent is by taking what? Logs on both sides. So that's what we're going to do here. I'm going to take the log of this side and the log of that side. Take the log of both of them. 6 to the x, 7 to the x minus 4. You're simply not going to solve these equations without logarithms. Not with any methods you know. So, Silvana, what next? What should I do now? Yeah, the power rule. So, these terms, these exponents come out in front. That one there, and this one here. For this one, I would put it in parentheses. So it's going to be x log of 6 equals x minus 4 log of 7. Now there's going to be two tricks in this one that you have to kind of follow to get this one right. Here's the first trick. And this one's probably the easier one to spot, easier one to come up with. What do you think we have to do next? Yeah, distribute. So we're going to distribute here. We can't get the x by itself until we start distributing. So let's do that. So thank you. X times log of 7 minus 4 times the log of 7. So I distributed that log of 7 term to both terms inside the parentheses. Okay? I want to get the x terms by themselves. So you need to move this to the left-hand side or this one to the right-hand side. It doesn't matter. I think I want to do it this way. I want to move this one over here and this one here. I'm going to kind of flip-flop them. And the reason being is that when I move this one to the left-hand side, what's going to happen to that minus 4? It becomes a plus 4. I'm going to end up with a minus either way, but I like trying to keep the negative signs to a minimum. So it's going to be 4 log of 7 equals, can someone tell me what's on the right-hand side? If you move that to the right-hand side, what's that going to look like? X log 7 minus, well done, thank you, x log 6. Nice. So we're down to the next one. We got 4 log 7 minus, or equals x log 7 minus x log 6. Here's where the second trick is. We're trying to get x all by itself. So, if you notice though, I've got x in two different terms here, right? I've got x here and I've got x here. I need to somehow bring that together. Here's our trick. X is a common factor. I'm going to factor that out. Log of 7 minus log of 6 times x. That's our trick. So factor out the x. So the first trick was to distribute. Second trick is to factor out the x. We're almost done. What's left? In order to solve for x, what's left? Abdul? Started saying it? Perfect. X is being multiplied by this number. It's an ugly number. It's probably something you never run across in your life again, but it's still a number. And the opposite of multiplication is division. So we'll divide both sides by that number. So log of 7 divided by, or 4 log of 7 divided by log of 7 minus log of 6 equals x. Okay. Are you okay with our steps on doing this one? I'll tell you what. A lot of times on exams, for certain problems or certain expressions, they'll say, calculate it. So why don't you see what you can calculate, and then we'll have some fun. We'll compare notes and find out, the different decimal values that you guys think this is equal to. So give that a shot, and then we'll compare notes. And I'll share with you a different way that you can calculate that maybe. So let's have some fun. Shane, what value are you getting for this? Oh. All right. Liz, what value did you get? Okay. Jared? All right. Anyone else get something different? Silvana? Okay. Morgan? You got the first one? So 2 votes here, 2 votes here. And you got the first one? Okay. Now, there's a couple ways you can calculate this. The problem with this one is that you have to be careful with the dividing part. So it's going to be 4 log of 7, right parenthesis, divided by, and now you need parentheses around the entire denominator. So it'd be parenthesis log of 7, right parenthesis, minus log of 6, right parenthesis, and then another right parenthesis to close off the bottom. So, yay, it looks like about 50.4397 is the winner. It's kind of a pain to calculate these things, though. So let me show you a couple different tricks. First of all, one that makes this a little bit less cumbersome is if you hit the alpha key, then the y equals key. That gives you a list of options. Just press enter, gives you the first option, and now you can type in your fraction just like you would normally. So it'd just be 4 log of 7, parenthesis, and then in the denominator, log of 7 minus log of 6. So not quite as cumbersome. Gives us the same thing. Looking good. Let me try and make this even easier for us. Oh, so again, those keys, when you press the alpha and then the y equals key, you'll get a list of different ways you can do fractions. So that one's just a regular fraction. This one would be a mixed number. So if I wanted to write in like 7 and 2/9, I could. So that's what that first one's for. Let's approach this using our skills and our rules of logarithms, though, just to make this easier. Remember, our product rule, or our power rule, says I can make this the exponent, right? This is a log of 7 to the 4th power. And in the denominator, what can I do different with log of 7 minus log of 6? Quotient rule. So log of 7 divided by 6. And a quick little bit of help here. I think 7 to the 4th power is 2,401. So this is log of 2,401 divided by log of 7, 6. So let's try that and see if that's easier to calculate. So log of 2401 divided by log of 7 divided by 6. Same thing. So one way or another, you have to be able to calculate it. And I've given you 3 different good ways you can work on this. It's whatever you find convenient. There are problems that I will ask for a decimal answer. If you look at last year's exams, and I don't think I have that page up, but if you look at the old exams, quite often I do ask for that kind of stuff. Yeah, I'll say calculate this value. Let me see if I've got an example from say last year's, I guess it'd be exam 5. Type exam 5. Ironically, we were going to do this one next. Yeah, right here. There it is. So if you take a look, I just say the solution to the equation is this. I give you the solution, and then I say calculate it. So you can calculate it from here, or here, or here, whichever way you find convenient. But the bottom line is you should be able to calculate it. Once you're done calculating it, in fact, let's have a little bit of extra fun or work with this. You can check that it works. So let's do it based on the last method, log of 2 divided by log of 1.5. So let me switch back over to here. So it's going to be the log of 2 divided by the log of 1.5. And let me do this. I'm going to take and store that. So lower left, store in x. So the variable x is right next to the alpha key, the green alpha key. Store that in x. So I'm not relying on the answer key now because I've got to store it in x. And let's go back to the equation. Where was it? There we go. So I want to compare 2 to the x plus 1 to 3 to the x. So 2 raised to the x plus 1 gives me this, and 3 raised to the x also gives me that. So you can feel pretty confident in your answer. I would just suggest that you might want to rearrange that a little bit in order to make it easier to plug into your calculator. Yes? Oh yeah, that's a good way too. Yeah, that's a clever way to do it. So going back to say this one, you could do 4 log of 7, press that and get the answer, and then hit the divide key, and it's going to automatically take your previous answer and say, okay, I'll divide that by whatever, and then you can do log of. Tell you what, let's do this form: log of 7 6. Log of 7 divided by 6. And again, we're getting that 50.493, etc. So, cool. Hopefully, one of those resonates with you as being a good way to solve that one. Any comments or questions on 34? What were the 2 tricks involved? What was the trick that we had to do right here at this step? Distribute. Distribute was the first trick. Then I moved things around. I wanted to get the x's on one side. I could have easily just moved things around to move this over here, and that would have put the x's on the left-hand side and left this on the right-hand side. I didn't do that because that would make this negative, and it just makes it a little bit more cumbersome to work with. So, and here was the second trick. What was the second trick? Factor out the x. Well done. Factor out the x. Well, let's do problem number 66, which was actually a problem on previous exam. To the x squared equals 11. Why don't you try and solve this one? This one works out pretty good. There is a little bit of an extra something at the end, but still should work out okay. Okay, so we'll start out on both sides by taking the log. So it's a log of 8 to the x squared equals a log of 11. The nice thing about taking logs is that we can use our power rule. So that exponent comes out in front. I sometimes call that the parachute rule because it feels like he's jumping out in front. X squared times a log of 8 equals a log of 11. Since we're trying to solve for x, I'll undo this multiplication with the division. X squared equals log of 11 divided by log of 8. How am I going to get x by itself? Square root on both sides. Log of 11 over log of 8. Now, there were several of you that I walked by and told you that he had a point or two left on the table still. Did anyone find out what was wrong with this answer? Not quite. Well done. Yes. You need the plus or minus. There's two possibilities, right? There's a positive and a negative. So you need both of them. And that's certainly going to be a point of credit on the exam. Have we done enough calculator work? We don't need to check this with a decimal value? Or do you want to get a decimal value there? No? Okay. That's fine. Let's take a big step back and look at problem number 22. So we're okay with 66? All right. Let's take a look at 22. 22. So 3 to the x plus 1 equals 27. Now I'll do this the traditional way first, and then we're going to go look back at this and see how we can make some improvements. And it won't be just this one that we can improve. We can improve a lot of these things as well. Typically speaking, we take the log on both sides, log of 27. The x plus 1 comes out in front. What would you do next? This is a lot like problem number 38. Yeah, divide by log of 3. So it's x plus 1 equals log of 27 divided by log of 3, which means x equals log of 27 divided by log of 3 minus 1. There's a little surprise for you on this one. Try calculating this number. See what you get. Second y equals, we'll do log of 27 divided by log of 3. And then you got to exit this and then do the minus 1. You can't subtract this and go, oh, that's log of 26 over log of 3. Nothing fancy like that happens. What'd you guys get? 2. Wow. After all the crazy numbers we've got this morning, it's kind of like, wow, a normal number, something I can put my hands on, 2. So it's kind of nice that we get 2. And you can check that pretty quickly, right? I mean, 2, 3 to the 2 plus 1 power is 3 to the third, which, hey, that's 27. It works. Now, I got an idea for us to make this problem a little bit simpler. And it'll make other problems like it simpler as well. So try and catch on to this if you can. Let's go back and look at 3 to the x plus 1 equals 27. Well, instead of taking the log base 10 on both sides, how about if I take the log base 3 on both sides? Log base 3 of 3 to the x plus 1 equals log base 3 of 27. That's kind of interesting. Now, there's a problem that I put on on this year's test that wasn't on last year's test, but you guys did really, really good on it. I was very, very happy. And let me see if I got a blank copy here I can put up. I don't. Do you mind if your writing is displayed on my YouTube channel? You got it right. Okay. All right. It's this one right here. You have log base 6. Log base anything of 1 is 0. Log base 4 of 7. Whoops. All right. In any case, what's happening here is that these things cancel each other out. So log base 3 of 3 to the x plus 1, what is that? X plus 1. So, wow, that's cool. And now this part over here, log base 3 of 27, let's see if we can't think about it. What power of 3 gives me 27? 3. Suppose you're not really good with exponents and logarithms. You're just like, What you could do with your fancy graphing calculator is hit the math key and then scroll up a little bit. Gives you the opportunity to log of any base. So log base 3 of 27. Oh yeah, that's 3. But take a look at how nicely this simplifies, right? X plus 3 equals 1, so what does x equal? Wow, that's really cool. We got this nice simplification because the exponent here and the base of the logarithm were the same, so they canceled each other out. It's just like up here, taking the square root of x squared. Those cancel each other out, and I get back to x. Ooh, bonus points here. What's the relationship between these two functions called? Or these two functions, exponent and logarithm? Anyone? They're inverse functions. What one does, the other one undoes. But in this case, choosing the base that matches the base of your exponent, boy, that made this problem a lot friendlier than the last one, right? I mean, the last one wasn't bad. Nothing really bad about this one, but boy, I think I like this one a lot better. So let's see if we can't do that one again, or use that idea again. Let's try problem number 38. Let's see if we can't use the trick that we just did. So this is 22. Revisited. Okay. So let's think. Don't fall asleep on me. Thank you. It was e to the 3.3t equals 9.1. Based on our example here, I'm going to take the log on both sides, but what base logarithm should I choose? E. I'm going to take the log base e on both sides. So log base e of e to the 3.3t equals log base e of 9.1. Okay, that's nice. By the way, typically speaking, people don't write log base e. Yes. Now the reason I wrote log base e is because on the left-hand side we're going to get some nice simplification. Ethan, how's the left-hand side going to simplify? Yeah. These cancel each other out. You just get the exponent. So Andrew, point well taken. Yeah, usually usually people don't write log base e, but I don't know. I hope that it helps you see this cancellation here. It still cancels, yes. So if I wrote ln of e to the 3.3t, it was still 3.3t. So it's just, I don't know how many of you would look at that and go, oh yeah, it's going to give me this. I mean, yeah, because the base is e. So it's up to you. If you're comfortable with that, hey, great. Write ln on both sides. I'm just trying to be user-friendly here. So ln of 9.1 divided by 3.3. There's your answer. Done. For giggles, let me calculate that. ln of 9.1, parentheses, divided by 3.3. And let's check that that works. I should be able to take that number and plug it into the original equation. So it would be e to the power of answer times 3, times 3.3. Oh. Wait a minute. Let's see here. Okay, so we got that. E to that power, power of answer times 3.3. Oh, you know what? I'm doing log base 10. Yeah, all right. That's all right. You said as much. You said you put log. I'm like, yeah, I needed log. Yeah, there we go. All right. There we go. 9.1. Whew. All right. The good thing is that I proved I'm human, right? How are we looking on 38? The important part is being able to simplify these logs and end up with that. Could you do this with log base 10? Absolutely. It'd look a little different, but it'd still get there. The only difference is if you did it with log base 10, for instance, your expression, you'd have log base 10 of 9.1 over 3.3 log base 10 of e. And that looks a little less fun to work with and calculate, but it's doable. Okay. Any other questions on 38? Yes. Oftentimes, it's only a few problems, maybe a couple problems where I say, give me a decimal answer. I think it would kind of slow down the flow of doing the exam if I had to give you, if you round in the nearest 10,000th on every single problem. So there's going to be one or two, and I showed you earlier, my last year's exam where I said, I just want to see you calculate one. There's probably a couple where you have to find that. Cool. All right, so we're going to break this up into two parts, the video, because this is getting kind of long. So I'm going to stop things here, and then we'll do the next part of this section, which is logarithmic equations. So we've conquered exponential equations. We'll actually go back and do a few more exponential equations today and again on Tuesday. We're going to spend a lot of time on this section. This is a challenging section, and I want to make sure that you've had enough practice with it. So good luck with it. Study hard.